do it. Let's solve this sucker. Following our order of operation, cry, pray, guess, solve. So you do the crying and the praying. I'll do the guessing and the solving. And you can do the guessing and solving with me. So the first thing we're going to do, like we've always done, we're going to rearrange the second order differential equation in terms of the reduced form. Okay? So that's going to go as following. So first I'm going to multiply through negative 2m over h bar squared through. Okay? So let's go ahead and do that. So when I do that, I can now just write the second derivative in psi of x. All right? And now that's going to be minus, and so the 2's and the 2's cancel because I'm multiplying it through, right? So now it's going to be minus m kf over h bar squared times x squared times psi of x, okay? And then now I'll show you that all of that equals, because remember I multiplied through the negative 2 over h bar squared all the way through. So now I get negative 2me over h bar squared psi of x, like we're normally used to seeing, okay? And so now, of course, rearranging this for the reduced form, I can write, right, just we're going to set all of this equal to 0. So minus, let's see here, kf over h bar squared times x squared times psi of x. And of course, now that's plus 2me over h bar squared psi of x, all equal to 0. Okay? And so now you've noticed here that I've got a couple of cheater things. So this is standard, I guess not really cheater things, things to make writing our equation a little bit easier. And so these are just, I know that we use lambda for wavelength, so that's not what's going on here. We don't have enough Greek letters, okay? And you're also going to see there's something, a bit of convenience, where we're going to call y equal to the square root of m times kf over h bar squared times x, okay? And so the reason why we're going to do that is because you notice that I got these constants right here, mkf over h bar squared times x squared, right? So if we replace all of this now, you know, if we use this simple notation, then I can replace all of this with just y squared. And so what's going to happen, we're going to rewrite our Schrödinger equation in a way that we can get rid of all of these constants. And we're going to switch letters. Don't worry, there's a reason for switching the letters, and we're going to come back to that in more detail, okay? So I'm going to switch to using y. And I'm going to write here second derivative of psi of y over dy squared, okay? Minus, and now I'm going to replace this whole thing by y squared, psi of y. And then now you notice I'm also going to use this lambda here, this 2me over h bar squared for lambda. So we can say plus lambda times psi of y, all equals 0. And now this should, being the key word, be a lot more easy to solve, okay? And of course, what we also need to build in is that asymptotic relationship we talked about, right? As psi approaches 0, as x approaches plus or minus infinity. So we're going to need to have solutions for y approaching infinity, okay? And so what that means is we need some type of asymptotic relationship. And this is the point where we could go through our normal guess solve methods, right? Where we guess e to the, in this case, it'd be e to the ay. But as it turns out, that's not going to give us this y approaching infinity asymptotic solutions, okay? And again, I'll remind you, asymptotic because, right, as this approaches infinity, we are going to have, you know, some cutoff, right? Some asymptotic relationship of where we don't expect it to have infinite displacement, okay? So what that means is our guess solution is slightly different than the guess solutions we've made before. And I'm also going to write this as a proportional or approximately equal to e to the plus or minus y squared divided by 2. So this becomes our guess solution. And this is kind of like the standard procedure in solving the harmonic oscillator problem. Okay? And so that gives us our E, all right? And what we're also missing to give it this asymptotic relationship here, we're going to say what we really need to get rid of this approximately equal to and make it a proper equality, we're going to say that we need some function in y, and then let's see, I'll say minus ey squared divided by 2. So we need this f of y, so this is a polynomial in y that's going to give us these asymptotic quantized values, okay? And so the simplest thing I can describe here, so I've got on my Mathematica file, I've got a whole number of polynomials right here, all right? And what these polynomials give us are definite quantized values where, in this simple example, where the polynomial crosses the x-axis, right? So I'm going to point out this purple one, right? We can see that it's crossing the x-axis at definite fixed values, okay? So that's going to give us that kind of cutoff, that asymptotic cutoff for our large displacement, all right? So this is going to become our guess solution. Psi equals f of y e to the negative y squared over 2. And the standard procedure is to ignore the plus solution because this e to the minus y squared, as we shall see, that describes a Gaussian distribution, which is also going to help us get a physically meaningful solution. Okay, so this is kind of the point in the class where we couldn't do this. We would have to really grind away trying to guess at a solution for a long, long time. And that's kind of beyond the scope of the class. So our guess, that's the standard guess for this harmonic oscillator problem. Okay.